Hello and welcome. Today we'll be looking at Otto cycle under gas power cycle. We have dealt with Carnot cycle. Alright, so what is an Otto cycle? An Otto cycle is also known as a constant volume cycle. Alright, so this Otto cycle, it is also used in a spark ignition engines or petrol engines. So we are going to be looking at the PV and the TS diagram of an Otto cycle, so that I'm going to explain the processes involved in an Otto cycle. All right, let's look at the PV and the TS diagram very quick. Right, the reason why I decided to show us how to draw it is because of our exam. So because any question under gas power cycle, you must draw the the PV and the TS diagram before you solve. All right. All right. All right. So here we are going to have P here. I love drawing this side by side. This is T. This is our S. All right. So we have P here. We have V here. All right. So here we have all right. So all right. I know maybe I should take it down. All right. So from here we have a TS diagram, which is just the opposite of what we have here. All right. So here we trace it down. Trace it down. We have 1, we have 2, we have 0.3 here, we have 0.4. All right. So here we are going to have 1 to 2 here. We have 3 to 4. So you trace this down as well. Trace this down as well. All right. So here we're going to have our maximum pressure here. Then here we are going to have P4. We are going to have P2 here. Then we are going to have P1. All right. So we have P3. We have P4, we have P2, and we have P1. We have P1. All right. So here we are going to have our S2, our V2 to be equals to V3. V2 is equals to V3. All right. So here V1 will be equals to V4. All right. So here we are going to have S1 to be equals to S2. We're going to have S3 to be equals to S4. All right. So here we have our maximum temperature here, followed by T2. Here we have our, all right, so we have our T4. Here we have our T1, T4, T2, and what? And T3. All right. So here, all right. So here we have this, we have this. So we have our PV gamma is equals to constant. All right. Now, next thing we have here is this. You need to put your arrow showing from 1 to 2. Moving from 1 to 2 is a cyclic. Moving to from 2 to 3, from 3 to 4, then from 4 to 1. Similarly with this. All right. So after that, we have our heat supply, quantity of heat supply. You can decide to put that one in any part of the PV or the TS diagram. So you can decide to put it here or here. So let's just maybe let's put it here. Let's put it here. So we have our heat supply here. Sorry, our heat supply, constant volume heat supply, and here we have our constant volume heat rejection. Here we have work done by compression, W subscript C, and here we have work done by expansion, this W subscript E. All right. So the next thing, I said you can decide to put this here too. Exactly. Anywhere you want to put it. So the next thing you need to consider again is these two places. All right. So here between V1 and V2, or V4 and V3, we have our stroke volume. That's what we call stroke volume. All right. So here we have our clearance volume. We have our clearance volume here. All right. So the whole thing now, from this point to this point, we now have total volume. Yeah, total volume. All right. All right. So this is everything that we have when it comes to our Otto cycle. So this is our PV. This one is our PV diagram. Let's write it down here. PV diagram. And this one is our TS. All right. So that is it. All right. So let's write all the four processes out from process 1 to 2. From process 1 to 2. Process 1 to 2 is nothing but what? It's nothing but adiabatic. It's nothing but adiabatic into slash isentropic compression process. All right. Adiabatic or and put this one in the okay, let's just put it as reversible. Let's put it in a complete more sense. Known as adiabatic. Reversible adiabatic. Reversible adiabatic into isentropic. I'll put it in brackets. Isentropic process. All right. So from process 2 to 3. From process 2 to 3, it is called constant volume heat supply. Constant volume. Or you can say reversible constant volume heat supply. Constant volume heat supply. Supply process. All right. So from process 3 to 4. From process 3 to 4. Process 3 to 4 is called reversible adiabatic. Reversible adiabatic into isentropic. Isentropic. This one is expansion. All right. Please, I did not put compression here. Sorry. I was busy looking for compression here. Compression process. Sorry, please. This one is expansion process. All right. So from process 4 to 1 now. From process 4 to 1 is called constant volume heat rejection process. Constant volume heat rejection process. All right. So these are all the 4 processes in an Otto cycle. All right. The meaning of all of this stuff is when air enter into the cylinder, it compresses it, right? So when it compresses it from process 1 to 2, then from process 2 to 3, a constant volume heat is being supplied. Then after that, it moved to process 3 to 4. From process 3 to 4, we said it is what? Reversible adiabatic expansion. That is, from process 3 to 4, it gets expanded. Exactly. It went to expansion process. And from process 4 to 1 now, it is being what? Rejected. So that is just how to explain these processes. All right. So, and the most important thing is for you to know how to draw the PV and the TS diagram, and you know all the processes. Then you know what an Otto cycle is. All right. So let's discuss about our stroke volume and our clearance volume. All right. Now you must note this, that under this topic, you must know that your compression ratio, from Otto cycle, from Carnot cycle, we said our compression ratio is nothing but what? V1 all over what? V2. All right. So, but here it is still the same, but now we are not going to be writing this in respect to what? In respect to stroke volume and compression and clearance volume. Please take note of that. Our V subscript S is our stroke volume. Our V subscript C is our clearance volume. Our V subscript T is the total volume. All right. So now, I'm going to take note. Compression ratio, which is denoted. It is denoted by sometimes you see in a textbook. Some textbook will write it as R subscript C like this. Some textbook they will write it like this, something like this. But let's just use this for the purpose of this class. All right, so let's use this. So is equals to what? Is equals to V1 all over what? V2, right? All right. So now, we also said that this is also equals to what? This is also equals to, it is also equals to the sum of stroke volume plus what? Plus our clearance volume. So it's also equals to VC plus VS all over what? All over clearance volume. So you must know this, where VC plus VS is our what? Total volume. Take note of that. So we can also rewrite this as total volume all over what? Clearance volume. All right, take note of that, please. So again, you need to note this formula, that our stroke volume can be denoted with this formula. All right, so our stroke volume is equals to pi all over 4 multiplied by d square L. All right, so L there is the length and d is in diameter. You can say it's the diameter of your clearance cylinder, your cylinder bore. Is that clear? Sometimes, while the length of length of stroke is just that we will not draw the diagram of a cylinder. If you know what a cylinder is, so that's what they are referring to here. So the diameter of the bore, or the diameter of the cylinder, and the length of the what? Of the cylinder. All right, so this is what you need to take note. We are going to be using all of this stuff to solve questions. So the next, our next topic now, our next video now will be on numericals. So we are going to solve close to 10 or 12 numericals. So stay tuned. We are going to touch all examples. All right, thank you, and I hope you have learned from this. Thanks.